Hello, we're still in Module 9, continuing our discussion of hypothesis testing, and now it's time to take up a test on a population proportion. Besides means, of course, we can do tests on proportions and other population parameters. And we've talked a little bit about proportions in earlier modules. We let P equal the population proportion. There are many situations where firms are interested in the proportion of a population that has some characteristic. For example, what proportion of the population is going to like a new product we come out with, or what proportion of people saw our most recent advertising campaign, and so forth. So there'll be many situations where we might want to test a hypothesis about that proportion. As usual, we have three different forms to the hypothesis. The hypotheses will now deal with P, the population proportion. We can have a one-sided right-tailed test, where the alternative says P exceeds P0, where P0 is the value in the null. You can have a one-sided left-tailed test, where the alternative says P is less than P0, or you can have a two-sided test, where the alternative says P is not P0. Remember, in all cases, the equality portion belongs in the null hypothesis. It might be a less than or equal or a greater than or equal, but we need the equals portion in the null. As usual, how do you know whether you have a one or two-sided test? Well, you have to read the problem and look at what it is you're interested in, and that will tell you whether or not to use a one or two-sided test and whether it's right or left-sided. As I said a minute ago, never forget that you need that equals portion in the null hypothesis, as we need a specific testing point in our null hypothesis. The alternative will be either a greater than, less than, or not equal to. We're going to see in a minute that the test statistic is actually very similar in form to the ones that we used when we did tests on means. Recall that our best estimator of a population proportion is P bar, our sample proportion. We talked about P bar in earlier modules. Recall that the distribution of P bar can be treated as approximately normal, provided n times P and n times 1 minus P are greater than or equal to the number 5, and we will assume that to be the case here. Here's the test statistic we're going to use. It's going to be a z-statistic. We'll take our sample proportion, P bar, minus the hypothesized value, over the standard error of the sample proportion. Now we're going to calculate sigma P bar a little differently than we did in an earlier module. We're going to calculate it as the square root of P0 times 1 minus P0 over n. You might recall when we did interval estimates that when we calculated sigma P bar, we used the square root of P bar times 1 minus P bar over n. So I asked the question over here, why do we use P0 and not P bar now in the denominator? Well, there's a reason for that. Remember that P0 is the value in your null hypothesis, and your null hypothesis is the maintained hypothesis. It's the hypothesis we tend to believe is correct unless we get strong evidence otherwise. So if the population proportion really is P0, then that's the correct value to use in this standard error. Plugging this into the denominator here gives us the entire formula here. Z is equal to P bar minus P0 over the square root of P0 times 1 minus P0 over n. I want to draw a similarity to this and the earlier formulas that we used, and you should see something in all of these formulas. Let's go back for a moment to when we were doing tests on means, and we had both the Z formula and the T formula. Notice what you're doing with this formula. X bar is our best point estimator, our sample mean. You're going to see how far away from the hypothesized value it is, and then you're dividing by the standard deviation, sigma over the square root of n. Basically, if you remember what z-values do, z-values count how many standard deviations away from the mean you are. In this case, when I take this numerator, x bar minus mu 0, and I see how far is x bar away from mu 0, I divide by the standard deviation. It's basically telling me how many standard deviations my sample mean is away from the population mean, or the hypothesized population mean. If that number of standard deviations is too large, we tend to reject the null hypothesis. If it isn't, we tend to not reject the null hypothesis. The same is true with this formula. The numerator is just saying how far is my sample proportion away from what I have in the null hypothesis. I divide by the standard deviation. That's basically saying how many standard deviations away is it. Again, if it's a large number, we'll reject the null hypothesis, and if it isn't, we can't. As usual, in hypothesis testing, we can use either the critical value approach or the p-value approach in making our decision. Let's start with the critical value method. With the critical value method, since we're using the z-distribution, we're going to find a critical z-value, which I'll call z alpha. That's the z-value that leaves alpha probability in the end of the distribution. If it's a right-tailed test, you're going to reject when you get a z-value above that critical value. If it's a left-tailed test, you're going to reject if you get a z-value below the negative of that z-value. And if it's two-sided, remember, we cut alpha in half, and we reject in both ends of the distribution. That is, we'll reject the null if z is above z alpha over 2, or if z is less than negative z alpha over 2. If we want to use the p-value method, remember, as always, we have a fairly consistent decision rule. We reject the null if the p-value is less than or equal to alpha. Remember that the critical value approach compares two z-values. The p-value approach compares two probabilities, alpha and the p-value. Let's do a problem. In 2010, surveys indicated that 60% of Americans favored greater regulation of firearms. A follow-up survey was taken in 2015 to see if that proportion had increased, due possibly to recent outcries over gun violence. In a sample of 300 Americans, 201 favored increased regulation of firearms. Test to see whether the proportion of Americans favoring greater regulation of firearms has increased since 2010. Use a 5% level of significance and show all parts of the test. Again, the first thing we have to pick up on in this problem is our hypotheses. Remember that many times a hypothesis test has a null hypothesis, that's the way something was in the past, and then the alternative hypothesis introduces something new, or possibly a change of what it was in the past. So in the past, 60% of Americans favored this greater regulation. Notice we're now interested in whether or not that has increased by 2015. So just the wording there tells you I want a one-sided test, and specifically it's going to be a right-tailed test. The null is simply going to say, is the proportion what it was in 2010? That is it still 0.6? Or has it increased above that 0.6 in recent years? So again, we have a one-sided right-tailed test. Let alpha be 5%. Let's calculate our test statistic. Remember, we'll need p bar, which is x over n. 201 over 300 is 0.67. Plug everything into our formula here, and you'll get a calculated z-value of 2.47. And by the way, I've rounded this slightly to 2 decimals. So if you do this on your calculator, you might get a slightly different answer, but that's nothing to worry about. If we're going to use the critical value approach, we need to compare that 2.47 to our critical value, which in this case turns out to be 1.645. And we'll look at that graphically in a moment. It's a right-sided test, so we're going to reject the null if our z-value is above 1.645. 2.47 is above 1.645, so we reject the null. And because of that, we are concluding that the proportion of Americans favoring greater regulation of firearms has increased since 2010. Diagrammatically, we look at our z-distribution. Our critical z, a z-value that leaves a 5% probability above it, is 1.67, or rather 1.645. Our calculated z was 2.47, which clearly falls into our rejection area. It's above 1.645, so we reject the null. If you want to use the p-value approach, remember our decision rule is always to reject the null if the p-value is less than alpha. Now we have to calculate the p-value. Since it's a right-tailed test and our calculated z was 2.47, we want to find the area above 2.47 on the standard normal distribution. Using a table or a calculator, you should get that to be about 0.0068. Again, you might get a slightly different answer there depending on how you rounded the 2.47 and whether you're using a calculator or a table. Again, we're going to get the same decision and conclusion as before. Since 0.0068 is below our alpha level, we reject the null. And we therefore conclude as before that the proportion of Americans favoring greater regulation of firearms has increased. Looking at this graphically, remember again that the p-value approach compares two probabilities, the alpha level right here, 5%, everything above 1.645, and the p-value, which we just calculated to be 0.0068. As long as the p-value is less than alpha, we are in the rejection area and therefore we reject the null hypothesis. If you would like to do this on your calculator, on a TI-83 or 84, press your Stat button, scroll over to Tests, scroll down to number 5 on my calculator, 1 proportion z-test. The number might differ depending on your model of calculator. Hit Enter. The calculator prompts you for the value in the null hypothesis for P0, which in this case is 0.6. X was 201, N is 300, and choose the right-tailed test option, P greater than P0, and go down and click Calculate. The calculator will give you the calculated z-value, 2.47 again, and the p-value of 0.006. Again, there may be some slight differences if you go out more than 2 decimals, but that's only due to rounding. Okay, and that's the end of part 4, and in the next part we're going to introduce a new distribution called the chi-square distribution.